The truth we ignored. Somewhere in the equations we already solved. The answer has been sitting there, not hidden, not theoretical, not waiting to be discovered, just ignored. Because the truth is this: interstellar travel is not impossible. It never was. The physics works, the math checks out, the mechanisms exist. We already know how to reach another star, and that should feel like good news, but it is. Because the moment you follow the solution all the way through, you realize something uncomfortable. The problem was never how to get there. The problem is what it takes to survive the journey, and more importantly, where the path actually leads. Tonight, we are not going to simplify anything. We are going to follow the physics exactly as it is. No optimism, no shortcuts, just the reality of what the universe allows, and what it demands in return. We are not waiting anymoa. There is a common belief that humanity is still waiting for a breakthrough. That one day, some genius will discover a new equation, a new engine, a new way to cross the stars, but that moment already happened, and nobody noticed, because the real answer didn't look like science fiction. It looked like engineering, quiet, uncomfortable, already solved. We have propulsion concepts right now that can, in principle, reach another star. Laser sails, fusion engines, even antimatter drives. Each one has been studied seriously. Each one has been modeled. And each one leads to the same conclusion: we can leave the solar system, we can reach another star within a human lifetime. So why haven't we done it? Because every solution breaks in the same place. Not in theory, but in reality, the first crack. Let's start simple. Imagine a spacecraft accelerating to 10% of the speed of light, not a fantasy number, a real one, about 30,000 kilometers per second. At that speed, distance starts to feel manageable. A nearby star becomes reachable. A journey becomes something a human could live through. It feels like we've solved it, until you look at what happens next. Because space is not empty. It looks empty. It behaves like empty at low speeds, but at high speeds, it becomes something else entirely. A medium filled with particles, dust, gas, atoms. At normal speeds, these are harmless. At relativistic speeds, they become lethal. When nothing becomes everything. Picture this clearly. You are inside a spacecraft, moving at 20% the speed of light. Ahead of you is darkness, no obstacles, no asteroids, nothing visible. It feels safe, but it is. Because scattered through that empty space are tiny particles, a single grain of dust, something you wouldn't even notice on your hand. At low speeds, it means nothing. At high speeds, it becomes catastrophic. At 10% of light speed, that tiny grain carries the energy of an explosion. At 20%, it's worse. Now imagine not one particle, but millions, billions, constantly, every second. Your ship is not traveling through space. It is being sandblasted by the universe at extreme energy levels, and there is no way to avoid it, because it is everywhere. The invisible wall. This is where every propulsion system hits the same wall. Laser sails. They reach the speed and then get destroyed by impacts. Fusion drives, same problem. Antimatter, even worse, because the faster you go, the more violent the environment becomes. The universe pushes back, not metaphorically, physically, relentlessly, and this is where the tone changes, because now the question is no longer, how do we go faster? The question becomes, how do we survive going fast? But before we go further, if you're into deep space, real physics, and ideas that completely change how you see the universe, make sure you subscribe, because what we're building here is not theory. It's the closest thing we have to a real roadmap to the stars, and it only gets stranger from here. The second problem, radiation. Even if you solve impacts, you're still not safe. Because there's something worse: radiation. At high speeds, radiation doesn't stay the same. It intensifies because of something called blue shift. When you move toward light, its energy increases, and at relativistic speeds, that increase becomes significant. Radiation that was manageable becomes dangerous. Radiation that was dangerous becomes lethal. Your shielding, no matter how advanced, was designed for normal space. But now, you're not in normal space anymore. You're in a transformed environment where every photon hitting your ship carries more energy than it should. The navigation nightmare. Now let's talk about something even less obvious. Navigation. At everyday speeds, navigation is simple. You see something, you react, but at relativistic speeds, that doesn't work because you're not seeing the present, you're seeing the past. Light takes time to travel, so everything you observe is already outdated by seconds, minutes, hours, depending on distance. At 20% of light speed, that delay becomes critical. You are moving fast enough that by the time you see something, you have already passed where it was. You cannot react. You can only predict, which means your entire journey depends on perfect calculations made in advance, no corrections, no second chances, the realization. At this point, something becomes clear. Every solution we have fails in the same way, not because the engines don't work, but because the environment becomes impossible. And that leads to a new idea, a different question. Instead of asking, how do we carry enough energy? We ask, what if we don't carry it at all? The shift. This is the turning point, because once you stop trying to carry energy, you start looking for it out there, already existing, already available. And when you do that, you find something powerful enough, something stable enough, something already operating at the scale you need. And that's where the story stops being comfortable. Because the answer is not a machine, not a star, not anything familiar. The answer, the part everyone ignores. There is a detail that almost every explanation of interstellar travel skips over. Not because it's unimportant, but because once you understand it, it makes everything harder, much harder. We like to imagine space as empty, a vacuum, a perfect silent void, but that's not what it is. Space is thin, but it is not empty, and that difference is everything. The ocean you can't see. Between the stars, there is something called the interstellar medium. It sounds harmless, almost insignificant. On average, it's just a few atoms per cubic centimeter. That's practically nothing. You could travel through it slowly and never notice it, but speed changes everything. At low speed, those atoms are background noise. At high speed, they become a storm. Let's make it real. At 20% of the speed of light, every hydrogen atom you hit is like being struck by a particle accelerator beam. Not once, but continuously, every second, for years. The energy you can't escape. Here's the part that breaks intuition. Energy doesn't disappear, it transfers. When a particle hits your ship, that energy goes somewhere, into your hull, into your shielding, into your systems. Even if you stop the particle, you don't stop the energy, you convert it into heat, into radiation, into damage. And this creates a problem that doesn't have a clean solution. Because every attempt to protect yourself makes something else worse, the shielding trap. You might think, just add more shielding. Thicker armor, stronger materials, more protection. But here's the problem. Every kilogram of shielding adds mass. More mass means more energy needed to accelerate. More stress on the structure. More exposure time in the dangerous environment. And this creates a loop. You add shielding, right arrow, ship gets heavier. Ship gets heavier, needs more energy. More energy, right arrow, longer acceleration. Longer acceleration, right arrow, more exposure. So you need even more shielding. And the cycle continues. There is no stable point, the equation that care. There is a formula that governs all of this. It's simple, elegant, and completely unforgiving. It's called the rocket equation, and what it says is this. To go faster, you need exponentially more fuel, not a little more, exponentially more. That means double your speed, right arrow, far more than double your fuel. Reach relativistic speeds, right arrow, absurd fuel requirements. At some point, it becomes impossible. Not technologically, physically, why every engine fails. Now we can see the full picture. Laser sails avoid carrying fuel, but still face radiation and collision problems. Fusion engines provide more energy, but still require massive fuel loads. Antimatter is incredibly efficient, but impossible to produce in useful quantities. Every solution solves one problem and runs into another, and all of them, without exception, fail at the same place, not because they are flawed, but because the universe is the real wall. This is the wall, the real one, not technology, not materials, not engineering. The wall is energy density. There is no way to carry enough energy to safely reach another star at meaningful speed, so the conclusion becomes unavoidable. The energy cannot come from the ship, the shift in thinking. This is where everything changes, because once you accept that, you stop designing engines and you start looking for power sources, not small ones, not manageable ones, but the biggest ones the universe has. And that search leads somewhere very specific, somewhere extreme, somewhere dangerous, somewhere that operates at exactly the scale you need, the only things powerful enough. Stars seem like the obvious answer. They produce enormous amounts of energy, but they spread it out in all directions. Over vast distances, they are powerful, but not concentrated. You need something else, something that doesn't just produce energy, but focuses it, something that converts mass into energy at extreme efficiency. And there are only a few things in the universe that do that. The answer you don't want. Black holes, not as mysteries, not as objects of fear, but as systems, because a black hole is not just something that destroys. It's something that processes energy. Matter falls in, and before it disappears, it releases enormous amounts of energy, more efficient than stars, more intense than anything we can build. And if it's rotating, it becomes something even more powerful. When destruction becomes useful, this is where the perspective flips. Everything we think of as dangerous about black holes is exactly what makes them useful. The extreme gravity, the radiation, the warped spacetime, all of it is part of the mechanism. And that leads to a strange realization. The only places in the universe powerful enough to enable interstellar travel are also the most dangerous places that exist. The pattern. At this point, a pattern starts to emerge. Every step forward comes with a cost. More speed, right arrow, more danger. More energy, right arrow, more instability. More power, right arrow, more risk. And eventually, you realize something unsettling. The universe is not blocking interstellar travel, it is filtering it. The filter. Think about what it takes to survive. Extreme radiation, constant high-energy impacts, perfect navigation, long-term isolation, zero margin for error. This is not just a technological challenge. It's a survival requirement. Any civilization that wants to travel between stars must first become capable of surviving the worst environments in the universe. That's the price of entry. The turning point. And now we reach the moment where everything changes. Because once you accept all of this, One idea becomes inevitable. If black holes already contain the energy you need, and space-time itself can be manipulated, then maybe you don't need to fight the universe. Maybe you can use it, borrowing instead of pushing. Instead of pushing a spacecraft forward with fuel, you let the universe push it. Instead of carrying energy, you extract it. Instead of resisting gravity, you use it. And that idea, that shift from force to geometry, is where things stop being difficult and start being strange. What comes next? Because the moment you start thinking this way, you discover something hidden in plain sight, something that has been in the equations for decades, something that changes interstellar travel from impossible to achievable when everything flips. Up until now, everything has felt like a dead end. Every solution fails, every path closes, every attempt to reach the stars runs into the same wall: energy, environment, survival, and then something changes. Not in the equations, but in how we read them. Because instead of asking, how do we build something powerful enough, we ask, what already exists that is powerful enough? Let's do the energy math. To understand what comes next, we need to talk about energy, not in vague terms, but in numbers, because intuition completely fails here. Chemical rockets, the kind we use today, convert almost none of their mass into energy. It's so small, it barely matters on a cosmic scale. Nuclear fission is better, fusion is better still. Fusion, the process that powers stars, converts less than 1% of mass into energy. And that sounds impressive until you realize something. That means over 99% of your fuel is wasted. Why even stars are not enough? The sun feels powerful. It lights up an entire solar system, but it's not efficient. It works because it's huge, not because it's good. If you tried to use stellar-level processes for propulsion, you would still fall short, because stars spread their energy out in all directions across enormous distances. You don't just need energy, you need concentrated energy, directed energy, usable energy, the number that changes everything. Now we arrive at the number, the one that changes the entire conversation. Black holes, specifically the material falling into them, can convert between 6% and 40% of mass into energy, not 0.7%, not 1%, up to 40%. That is not an improvement. That is a different category. It means black holes are the most efficient energy engines in the universe, not by a little, by a massive margin. What a black hole really is. Most people think of black holes as simple, just objects that pull things in, destroy them, end of story. But that's not what they are. A black hole by itself is actually quiet, almost invisible. The real action happens around it. When matter falls toward a black hole, it doesn't fall straight in. It spirals, forms a disk, accelerates, collides, heats up, and that process releases energy on a scale almost impossible to imagine. The brightest things in the universe. Some black holes are surrounded by massive accretion disks. These disks glow, not softly, violently. They emit radiation across the entire spectrum: X-rays, gamma rays, ultraviolet, radio waves. All at once, some of these systems outshine entire galaxies. Think about that. One region of space, brighter than billions of stars combined. And it's not a star, it's matter falling into a hole. The moment you can't unsee. Once you understand this, you can't unsee it. Black holes are not just destructive, they are engines, natural ones, already running, already stable, already operating at exactly the scale we need. And that raises a question that changes everything. If they already produce this much energy, Can we use it? Rotation changes everything. Now we add one more ingredient, rotation, because real black holes don't just sit still. They spin, and when they spin, they do something extraordinary. They drag space-time itself, not metaphorically, literally. Space around them starts moving. When space starts moving. Imagine standing near something where space itself is being pulled, where direction is no longer yours to choose, where motion is forced. That region exists. It's called the ergosphere. Inside it, you cannot stay still. No matter what you do, space itself carries you, and this is where physics breaks intuition. Because inside this region, something impossible becomes possible. The impossible trick. Inside the ergosphere, you can extract energy from the black hole, not by breaking laws, but by using them. You send something in, it splits. Part falls in, part escapes, and the part that escapes comes out with more energy than it went in with. That extra energy comes from the black hole. The black hole is a battery. This changes everything, because now the black hole is not just an object. It's a system, a reservoir, a battery, a machine, and the universe already built it. No engineering required, no construction needed, just there, waiting. The next step. Now we take one more step, because particles aren't the only thing that can interact this way. Light can too, and near a black hole, light does something strange. It bends, not slightly, extremely. So much that it can orbit. Light that goes in circles. There is a region around a black hole where light can travel in circles, not escape, not fall in, just orbit forever. This is called the photon sphere. And it is one of the strangest places in physics, because it means something fundamental changes. The straightest possible path is no longer straight. This is where it starts. Now think about this carefully. If light can loop around a black hole, then a beam of light, a laser, does not travel in a straight line anymore. It curves, it bends, it can return. And if the black hole is moving, something even stranger happens. The energy comes back. When light interacts with a moving gravitational field, it can gain energy. The same way a ball bouncing off a moving wall comes back faster. The light returns, stronger, more energetic, and that extra energy came from the black hole's motion, the realization. Now everything clicks into place. You don't need fuel. You don't need propulsion. You don't need to carry energy. You can borrow it from the motion of black holes, from the structure of space-time itself. The first glimpse of the solution. This is the moment where interstellar travel stops being impossible. Not because we invented something new, but because we understood something that was already there. A system, a mechanism, a method, hidden in the equations the entire time. And this is where it gets uncomfortable. Because once you see this, you realize something else. The only places where this works are the most dangerous places in the universe. Near event horizons, near photon spheres, near regions where space itself breaks normal rules. There is no safe version of this. The question changes again. So now the question is no longer, can we reach the stars? The answer is yes. The question is, the moment the equations turn into a road. Everything we've talked about so far has been building to this. Not a theory, not a possibility, but a mechanism, something you can actually do if you have the technology, if you can survive the environment, and if you understand the geometry, because this is the point where interstellar travel stops being about force and becomes about timing, position, and precision. The core idea simplified. Let's strip this down to the simplest possible version. You have a spacecraft. On that spacecraft, you have a powerful laser ahead of you. There is a black hole, not directly in front, not something you're flying into, but something you are using. You fire the laser, the beam travels forward. But instead of continuing straight, it curves, it bends around the black hole, loops, and comes back. Why the beam returns? This only works because of one thing. Space-time near a black hole is curved, so curved, that what we think of as a straight line is no longer straight. Light follows the shape of space, and near a black hole, that shape loops. So if you aim correctly, your laser beam comes back to you, the detail that changes everything. If the black hole was standing still, nothing special would happen. The beam would return with the same energy it left with, no gain, no advantage. But black holes are not still, they move, and more importantly, many of them move in pairs, orbiting each other at incredible speeds, the moving mirror. Now imagine this. Your laser beam travels around a black hole. While that black hole is moving, the gravitational field that bends your beam is also moving, and that changes everything, because when light interacts with a moving system, it can gain energy. Exactly like a ball bouncing off a moving wall, it comes back faster, the energy transfer. When your beam returns, it carries more energy than before, not because you added energy, but because it borrowed energy from the motion of the black hole. And when your spacecraft absorbs that beam, it gains momentum, it accelerates without using fuel. This is the halo drive. This is the mechanism. This is the name, the halo drive. Because the path of the laser forms a loop, a halo, around the black hole, and through that loop, energy is transferred from the black hole to your spacecraft. Why this works? This doesn't break physics, it follows it. Energy is conserved. Momentum is conserved. The black hole slows down by an amount so small, it's practically unmeasurable. Your spacecraft speeds up by an amount that matters. The system balances, the universe allows it. The scale of the effect. This is where it becomes hard to fully grasp, because the amount of energy involved is enormous. A single interaction can provide meaningful acceleration. Repeated interactions can push a spacecraft to a significant fraction of the speed of light, up to around 20%. That number again, 60,000 kilometers per second. What that speed really means. At that speed, distance changes. The moon a few seconds away, the sun, minutes, the outer planets, hours, nearby stars, decades. For the first time, interstellar travel becomes something real, something measurable, something possible. No fuel, no rocket equation. And here's the most important part. You don't carry fuel. You don't fight the rocket equation. You don't need massive propellant tanks. The energy comes from outside, from the universe itself. Which means you break free from the biggest limitation of all previous designs. This changes the problem. At this point, interstellar travel is no longer an energy problem. It becomes something else entirely. A positioning problem, a navigation problem, a survival problem, because now, the only thing standing between you and the stars is whether you can actually reach and operate near a black hole, the first real obstacle. And this is where the optimism stops. Because the halo drive doesn't remove danger, it concentrates it. Everything that makes the system work is exactly what makes it lethal. The proximity, the radiation, the gravity, the instability, you cannot separate them. How close you really have to be. To make this work, you need to operate near the photon sphere, that region where light bends into loops, and that region is extremely close to the event horizon, not millions of kilometers away, not even thousands, tens of kilometers. That's it. a tiny margin between you and the point of no return, the margin that exists. Think about that, a spacecraft operating at relativistic precision, within a few tens of kilometers of the most dangerous boundary in physics, where one mistake is final, there is no recovery, no correction, no second attempt, the environment you can't escape. At that distance, everything is extreme. Radiation levels that destroy electronics, tidal forces that stretch structures, gravitational distortions that change motion itself. This is not a place designed for survival. It's a place designed to end things. And yet, this is exactly where you need to be, the inescapable truth. This is the part that defines everything. You cannot use the halo drive safely. There is no safe version. There is only a working version and a non-working version. And the working version exists inside the most hostile environment in the universe, the trade. So now the trade becomes clear. If you stay safe, you stay home. If you go to the stars, you accept the risk, not small risk, not manageable risk, extreme risk, fundamental risk, the kind that defines civilizations, the second realization. And now something even more unsettling emerges, because once you understand this mechanism, you realize something else. Black holes are not rare, they are everywhere. The network starts to appear. There are millions of black holes in our galaxy, many of them in binary systems, moving, orbiting, exactly the kind of systems the halo drive needs. Which means something important. The infrastructure already exists. This is not a single path. This is not one route, not one location, not one opportunity. This is a network, a distributed system spread across the galaxy. A set of natural nodes that can be used to move, and that changes everything again. Because now interstellar travel stops being about distance and starts being about routing. Where are the black holes? How are they moving? Can you move from one to the next, the beginning of something bigger? This is where the idea expands, because once you see black holes as energy sources, you stop seeing them as obstacles and you start seeing them as infrastructure, nodes, waypoints, gateways, the question no one asks. And now we arrive at a question that is hard to ignore. If this system exists, and the physics allows it, then someone else could have found it, used it, the moment distance stops mattering. Up until now, we've been thinking about interstellar travel the wrong way. We think in distance, light years, trillions of kilometers, unimaginable gaps between stars. And when you look at it that way, it feels impossible, but that's the mistake, because distance was never the real problem. The ocean analogy. Think about early ocean travel. The first ships that crossed vast oceans didn't succeed because the ocean got smaller. They succeeded because they understood the currents, the winds, the energy already present. A ship that fought the ocean failed. A ship that used it crossed it. Apply that to the galaxy. Now take that idea and apply it to space. If black holes are energy sources, and the halo drive lets you use them, then the galaxy is not empty, it's structured not by distance, but by access. The first glimpse of the network. Instead of asking, how far is the next star? You ask, where is the next usable black hole? And suddenly, the map changes. The galaxy stops being a void and starts becoming a network. 100 million nodes. Our galaxy alone contains around 100 million black holes, not guesses, not theories, estimates based on stellar evolution. That means millions of potential energy sources, millions of possible waypoints, millions of places where the halo drive could work, but they are not random. Here's the important part. They are not evenly distributed. They cluster because they come from stars. And stars don't form randomly. They form in regions, dense regions, active regions, which means black holes. Follow patterns, the shape of the network, along the spiral arms of the galaxy. Black holes are more common near the galactic center. They are extremely dense in the outer regions. They are sparse, and this creates something very specific, not a uniform field, but a network with dense hubs, connected corridors, sparse dead zones, highways and deserts. Some regions of the galaxy are like highways, dense with nodes, easy to move through, multiple routes, multiple options. Other regions are deserts, few nodes, large gaps, no clear path, and in those regions, interstellar travel becomes much harder. Routing replaces distance. This is the key shift. Travel is no longer about going straight, it's about going efficiently. You don't aim directly at your destination, you aim for the next node, then the next, then the next, just like stepping stones. The strange consequence. This leads to something strange. A closer star might be harder to reach than a farther one, because if there's no usable black hole nearby, there's no path, but a distant system, connected by multiple nodes, becomes easier. Distance stops being the main variable. Connectivity replaces it, the galactic hub. Now consider the center of the galaxy. At its core, there is a supermassive black hole, surrounded by dense clusters of stars and smaller black holes. This region is the most connected place in the galaxy, the ultimate hub, the intersection of countless routes. The most dangerous place is also the most important, but it's also the most hostile. Radiation, gravity, instability, extreme conditions, everything we would want to avoid. And yet, it's the most valuable location in the network, because every path can pass through it. This pattern should feel familiar. This is not new, it's exactly how networks behave. On Earth, ports become cities, trade routes define power, access determines growth. In the galaxy, black holes become nodes, routes define expansion, access determines movement. A civilization would not expand evenly. Now imagine a civilization using this system. It would not spread outward in a perfect sphere. It would follow the network, expanding along dense corridors, avoiding sparse regions, filling the galaxy in a pattern that looks uneven, fragmented, non-uniform. The map would look strange. From a distance, it wouldn't look like expansion at all. It would look like clusters of activity, disconnected regions, empty gaps, not because nothing is there, but because nothing is connected. And now the question gets serious. Because once you understand this, you realize something uncomfortable. We've been searching for signals, radio waves, megastructures, obvious signs of intelligence. But what if that's not what we should be looking for? What if we are looking in the wrong way? A civilization using black hole networks wouldn't necessarily broadcast, wouldn't necessarily build visible structures. It would move quietly, efficiently, along routes we don't even recognize. The silence changes meaning, and that changes the meaning of silence, because silence no longer means there is nothing out there. It could mean they're not here. The highway you can't see. Imagine standing in the middle of nowhere, no roads, no traffic, nothing moving. You might conclude there are no cars, but you'd be wrong. You're just not on the road. Apply that to US. Now apply that idea to Earth. We might not be in a dense region of the network. We might not be near major routes. We might not be near important nodes. We might simply be off the path, the possibility no one likes. And if that's true, then the galaxy could be active, moving, connected, alive with travel. and we wouldn't see any of it, because none of it passes through here. The filter reappears. This connects back to something we touched earlier, the filter, because not every civilization reaches this stage. To use this network, you must survive extreme environments, master relativistic navigation, operate near black holes. That's not easy, that's not guaranteed, that's a filter. Who makes it through? So there are two possibilities. Either no one has reached this level yet, or some have, and they moved on into the network, leaving behind regions like ours that are not connected, the beginning of a different answer. This is where the question of where is everyone changes. Because maybe we're not early, maybe we're just not connected, the next step. And now we take one final step forward, because understanding the network is not enough. We need to understand what it actually takes to use that network is the part no one likes to linger on. It is easy to say that black holes could become infrastructure. It is easy to say that a civilization might route itself through the galaxy by moving from one gravitational node to the next. It is easy to look at the equations from a safe distance and admire how elegant the system is. But elegance is deceptive. The closer you get to the actual environment that makes the halo drive possible, the more the idea changes tone. It stops feeling like a clever solution and starts feeling like a test, a brutal one, because the truth is that the engine and the danger are the same thing. That is the reality at the center of this entire story. There is no safe layer beneath the mechanism. There is no comfortable version of this concept hiding behind the equations. The very same features of a black hole that make it useful are the features that make it almost impossibly hostile. The curvature of spacetime that bends your beam is the same curvature that can drag you into the point of no return. The energy-rich environment that makes the system worth approaching is the same environment that can burn through electronics and flesh alike. The proximity that gives you an efficient maneuver is the same proximity that leaves no room for recovery if anything goes wrong. You do not travel to the stars by discovering a safe road. You travel to the stars by learning how to survive the road that already exists. And that road passes straight through the most violent conditions nature can produce. Think about what the halo drive actually requires. Not in abstract language, not as a diagram in a journal article. Think about it as a real operation, a real spacecraft, real systems, real matter, something built by a civilization that wants to live long enough to leave home and still arrive somewhere else intact. The ship has to approach a black hole closely enough that its laser can curve through the warped geometry near the photon sphere and return with an energy boost. That means it is not operating comfortably far away. It is not standing off at some respectful distance the way we observe astronomical objects through telescopes. It is moving into a regime where spacetime is no longer behaving in ways any ordinary engineering tradition was built to handle. This matters because engineering is always local. It is always shaped by the environments in which it developed. Ships built for oceans fail in vacuum. Aircraft built for atmosphere fail underwater. Machines built for Earth fail in deep space. Every tool reflects the world that taught its builders what counts as normal. And nothing about the vicinity of a black hole is normal. Near a stellar mass black hole, the margins are absurdly small. The event horizon of a black hole, a few times more massive than the Sun, is not some giant boundary stretching across millions of kilometers. It is compact, tight. The photon sphere sits only a short distance beyond it. The geometry you need to exploit exists right next to the geometry that ends you. There is no generous buffer zone, no easy staging area, no region where you can calmly pause and check your work. You are operating on the edge of a gravitational cliff, and gravity near that cliff does not act gently. Tidal forces become real in a way that human intuition is simply not built to understand. On Earth, tidal forces are something we associate with oceans and shorelines, with the moon tugging on water. They are background effects, soft, broad, easy to ignore. Near a black hole, tidal forces stop being a background effect and become an active structural threat. Different parts of your spacecraft are being pulled with measurably different strength. The nose feels more gravity than the tail. One side experiences a slightly different geometry than the other. The result is stretching, compression, stress distributed through the frame in ways that no ordinary vehicle would ever need to survive. That means every beam, every joint, every shield layer, every internal support is under continuous strain. Not from motion through air, not from engine vibration, but from the shape of spacetime itself. The environment is trying to pull your craft into alignment with a geometry that does not care whether your materials remain intact. And if you are close enough for the drive to work efficiently, those forces are not optional background complications. They are part of the operating conditions. Then there is radiation. This is where the idea begins to feel openly hostile. A black hole by itself can be quiet, yes, but a black hole useful enough to matter as a propulsion node is very often not alone in perfect darkness. It exists in a real astrophysical setting. Gas, dust, disrupted matter, companion objects, orbital debris, plasma, all of it interacting, all of it heating, all of it creating an environment saturated with high-energy emissions. If there is an accretion flow, even a modest one, the radiation can become intense enough to turn the surrounding region into a killing field. And this is not the kind of danger you solve with a simple wall. Radiation at these energies penetrates, it ionizes, it degrades circuits, it scrambles memory, it weakens materials at the atomic level, it turns the inside of your spacecraft into an ongoing battle between shielding mass and survivable exposure. Add more shielding and your ship becomes heavier. Make the ship heavier and the maneuver becomes less efficient. Less efficient means more time near the source. More time near the source means more radiation dose. More radiation dose means more shielding. The problem folds back into itself. Everything about this system creates loops like that. Every solution has a cost that strengthens the original problem. That is why the halo drive is so unsettling. It does not offer a free escape from the old limits. It just moves the limits. The rocket equation dominated conventional propulsion because you had to carry your energy with you. The halo drive escapes that trap by borrowing energy from moving black holes. But in doing so, it throws you into a place where mass, shielding, structural tolerance, navigation precision, and exposure time become entangled so tightly that you are solving a whole new class of impossibility. And the deeper you look, the more they stop feeling like separate problems. Because they are all expressions of one thing, the universe does not hand out interstellar access casually. Even the navigation is cruel. It is not enough to get near a black hole, you have to get near it correctly. Position matters, angle matters, timing matters, velocity matters. The returning beam has to follow the right path through curved spacetime. Your craft has to receive that beam without drifting into a fatal trajectory. The black hole, if part of a binary system, is moving. The companion is moving. The geometry is dynamic. You are not using a machine that sits still and behaves the same every time. You are using a cosmic process in motion, one that changes continuously according to orbital dynamics you must predict with ridiculous accuracy. And unlike a normal engineering environment, you do not get to practice with low stakes. You do not test a little closer, then a little closer again, refining as you go. Near a black hole, the first major mistake is also the last one. That changes what technology means in this context. We tend to imagine advanced civilizations as simply having better versions of what we have. Stronger materials, more powerful computers, smarter automation. But that is not enough here. To operate a halo drive routinely, a civilization would need a whole different relationship with error, different design philosophy, different thresholds for autonomy, different standards for reliability. Systems would have to function under conditions where maintenance is impossible, rescue is meaningless, and communication delays erase the idea of outside help. If something fails, the ship deals with it alone or not at all. That isolation matters more than people realize. When humans think about exploration, we instinctively imagine connection, mission control, backup plans, engineers watching telemetry, someone back home helping interpret the unknown. Interstellar travel strips that away. The farther and faster you go, the more complete the separation becomes. A spacecraft attempting a high-risk maneuver near a black hole is not an extension of a civilization's infrastructure in the ordinary sense. It is its own civilization in miniature. It has to be self-contained, self-correcting, self-diagnosing, self-saving, because the outside world is too far away to matter on operational timescales. That means the challenge is not just building ships. It is building worlds small enough to fly. Worlds that can think, decide, repair, endure, and continue under conditions where no outside voice can reach them in time to make any difference. And once you accept that, another realization begins to settle in. Any civilization that actually uses the black hole network is not merely technologically advanced. It is psychologically transformed, culturally transformed, maybe even biologically transformed. Because a civilization does not build machines like this without changing itself in the process. You do not normalize operation near event horizons and remain the same kind of species that evolved under a quiet sky and gentle gravity. Whatever crosses that threshold has learned not only how to engineer against destruction, but how to organize its priorities around environments that would look insane to anyone still planet-bound. That is why the filter matters so much. If the road between the stars runs through black holes, then interstellar civilization is not just about intelligence, not just about curiosity, not even just about time. It is about surviving a very specific set of extreme conditions. It is about discovering whether your species can make the transition from building tools for safe environments to building identities around unsafe ones. And many civilizations, maybe most, may never do that. They may solve energy, they may solve computation, they may solve long-duration habitats, but if they cannot survive photon-sphere distances from black holes, they never reach the highway. They stay local, they remain brilliant perhaps, powerful perhaps, long-lived perhaps, but local. And the galaxy remains silent to them, not because it is empty, but because the doors between regions only open for those willing to step into places that look indistinguishable from death. That gives the silence a different character, not loneliness, selection, and it also suggests something even more unnerving. If there are civilizations out there that did pass through this filter, then their visible behavior may be nothing like what we expected. We tend to imagine advanced life announcing itself, spreading obvious signals, building giant visible monuments. But a civilization organized around black hole infrastructure may look almost invisible from the outside. Its most important activities would happen in places we can barely observe, near dense gravitational regions, along routes defined by invisible topology rather than visible geography. Its traffic would follow black hole corridors, not star maps. its priorities would center on access to nodes, not merely possession of territory. Its expansion would look patchy, asymmetric, corridor-bound, concentrated near high connectivity zones, and absent from vast stretches of ordinary-looking space. From far away, it may not look like expansion at all. It may look like noise in the wrong data set, a merger rate slightly off expectation, orbital parameters that drift strangely, accretion patterns that do not quite fit the natural model. The signature of intelligence might already be mixed into our astrophysics, not in the form of messages, but in the form of systems behaving just subtly differently than untouched systems should. And we may not notice because we are still listening for voices instead of traffic. But before we go that far, it is worth staying with the immediate truth. The halo drive is not frightening because it sounds exotic. It is frightening because it sounds plausible. That is the difference. Warp drives are dramatic, but depend on physics we do not know how to realize. Wormholes are fascinating, but remain entangled with conditions that may never exist in the real universe. The halo drive is nastier than either of them because it uses known physics, curved spacetime, moving black holes, gravitational lensing, energy transfer through geometry. None of this is magical. None of it asks the universe to become stranger than it already is. It only asks whether something built by intelligence can endure the environments where those known effects become useful. And that is a much more uncomfortable question because it does not let us dismiss the idea as fantasy. It just asks whether we are tough enough, not smart enough, tough enough. There is a difference. A civilization can be brilliant and still fail this test. It can understand the equations perfectly and still refuse the environments they point toward. It can see the road clearly and decide that any road beginning next to an event horizon is a road not worth taking. In that sense, the black hole network is more than infrastructure. It is a kind of judgment embedded into physics, not a moral judgment, not a conscious one, but a structural one. It divides civilizations not by knowledge, but by tolerance for extremity. That may be why the idea feels so sharp. It is not just telling us how interstellar travel might work. It is telling us what kind of beings are likely to achieve it. Beings willing to build their future in places where the line between engine and execution method nearly disappears. Beings that have engineered away the fear of operating in the very environments evolution should have trained them to avoid at all costs. Beings for whom a black hole is not primarily a symbol of doom, but a resource, a port, a machine, a stepping stone. And once that possibility becomes real in your mind, it changes the way the galaxy looks. Every quiet binary system becomes more than an astrophysical curiosity. Every region dense with stellar remnants becomes more than a graveyard of dead stars. It becomes potential infrastructure, potential traffic, potential history. The entire Milky Way begins to resemble something we have not yet learned how to read properly. Not a random scattering of stars in a void, but a structured environment where the deepest roots are written in gravity, not light. Which brings us to the next unsettling step. Because if black holes are the nodes, then the galaxy is not just a map. It is a transit system. And once you start thinking that way, you begin to wonder whether the sparse, quiet region around us is not the center of the story at all. It may just be the shoulder of the road. And that possibility is where the whole question turns from engineering into philosophy. Because if the roots are real, and if the filters are real, and if access depends on surviving environments like these, then the emptiness we feel when we look outward may have never been evidence of absence. It may only be evidence of location. We may be standing in a place the network barely touches, asking why we do not see movement, while the movement happens elsewhere along corridors of black hole infrastructure we only just learned to imagine. The road exists, but existence is not invitation. Not every civilization reaches it. Not every star system lies near it. Not every species survives the price of entry, and that is the coldest part of all. The universe does not forbid the crossing. It simply makes the crossing contingent on a kind of endurance so extreme that most minds, reading the requirements honestly, recoil from them. The stars are not locked away behind impossible physics. They are guarded by conditions. Conditions sharp enough to look like a wall until you realize they are really a gate. A gate made of tidal stress, lethal radiation, relativistic precision, total isolation, and the demand that your machines continue operating where common sense says nothing built by life should function. If you can live there, you pass. If you cannot, you remain where you were born. And maybe that is the answer that has been hiding under all of this from the beginning. Not that the universe is empty, not that interstellar travel is impossible, but that the path outward is so specifically hostile that only a narrow class of civilizations will ever take it. And those civilizations, once they do, will route themselves through black holes and galactic hubs and dense corridors of gravity-rich infrastructure, becoming harder to recognize the farther they move from the assumptions of the world that first imagined them. The farther we follow this logic, the stranger the silence becomes, because silence in this picture is not peace. It is distance from the dangerous places, and once you understand that, another possibility begins to take shape, quietly at first, then all at once. If the black hole network is real, and if the price of using it is as extreme as the physics suggests, then the galaxy may not be silent in the way we have always imagined. It may only be silent to the kinds of searches we know how to perform. That distinction matters. It matters a lot. Because for decades, when we asked whether anyone else was out there, we framed the question in a very specific way. We listened for radio signals. We searched for pulses, patterns, mathematically clean messages, the sort of thing a civilization might broadcast if it wanted to be found. We looked for giant visible engineering projects, for stars dimming in unnatural ways, for signatures so obvious that they would announce intention from across interstellar space. But a civilization that travels by black hole infrastructure may not leave behind those kinds of signs at all. It may have no reason to. A species that has solved the problem of moving through the galaxy by routing along gravitational nodes is not a species that needs to shout into the dark. It does not need to paint the sky with giant beacons or spend energy on spectacular displays for distant strangers. Its most important actions would happen where the energy is, near black holes, near dense gravitational environments, near regions we are only now learning how to observe properly. That means the visible footprint of such a civilization may not be a signal. It may be a pattern hidden inside astrophysical data we have been classifying as natural simply because we did not yet know what else to call it. And that idea is more disturbing than the old one, because it suggests the evidence might not be absent, it might be misfiled. Think about gravitational waves for a moment. We only recently became capable of detecting them at all. A century after they were predicted, we finally built instruments delicate enough to measure distortions in spacetime smaller than a proton across kilometers of detector length. That alone should recalibrate our sense of how young our observational civilization really is. We are not veteran listeners in a well-studied universe. We are infants who just learned that space itself can ring like a bell. And what did we hear first? Black holes, binary systems spiraling inward, mergers, violent releases of energy carrying away the final record of orbital motion that took millions or billions of years to build. We heard death certificates. That is what the first detections really were. Not the lives of those systems, but their endings. The last fraction of a second in a process unimaginably long. And if that is the first page of the book we managed to open, how much of the rest of the book have we not read yet? Because if interstellar travel depends on accessing the orbital energy of binary black holes, then gravitational wave astronomy becomes something more than a new tool for studying exotic astrophysics. It becomes, potentially, the first instrument capable of noticing traffic on the real roads of the galaxy, not directly at first, not in some cinematic, undeniable way, more subtly than that. You would not necessarily expect a civilization using halo drive-like maneuvers to leave behind giant, obvious scars on a black hole system. The energies involved are enormous, and the systems themselves are massive beyond ordinary comprehension. But too small to notice is not the same as impossible to detect forever, especially if the activity is repeated, structured, and distributed across the network. Over time, the signatures might accumulate into something statistical, something that makes the natural distribution look just slightly wrong. A merger might happen sooner than expected. An orbital decay rate might drift from the clean curve predicted by gravitational wave emission alone. A binary might show dynamical features that fit no tidy natural model, as though something had been repeatedly borrowing from its momentum budget and paying it back unevenly. Not enough to leap out immediately as artificial, but enough to create a residue of unease, enough to make the data feel stubbornly untidy. And that is exactly the sort of place where truly important discoveries often hide. Not in the spectacular anomaly everyone sees at once, but in the persistent mismatch between what the theory says should happen and what the universe insists on doing instead. The reason this matters is that we have spent most of our search for cosmic company looking for intention expressed in familiar forms. Signals, messages, monuments, but infrastructure does not necessarily behave like a message. A road is not trying to speak to you. A port does not exist to announce itself to inland villages. A transit system has its own logic, and most of that logic is indifferent to anyone standing far outside it. If black holes are ports, if binaries are acceleration nodes, if galactic hubs are what organize motion at scale, then the traces of civilization may resemble logistics more than language. And logistics are easy to miss if you are listening for a voice. That brings the question back to us in a more uncomfortable form. Not where is everybody, but what if everybody who made it far enough stopped behaving in the ways we expected intelligence to behave? What if the mark of maturity in a galactic environment is not broadcasting, but routing? Not spectacle, but access. Not centralized empire glowing across the sky, but movement through corridors of invisible structure, optimized over time by species that learn the galaxy is easier to traverse than to illuminate. That would explain something important about the emotional shape of the cosmos as we experience it. We keep expecting the universe to look inhabited in ways that feel socially legible, as though advanced life would inevitably leave behind the cosmic equivalent of city lights. But perhaps interstellar civilization is less like an illuminated city and more like a freight network running at night through regions too distant for the villages nearby to see. Real, active, essential to those inside it, almost invisible to those outside it. And if that is true, then our location matters more than our intelligence. That is another one of the hard conclusions hidden inside this idea. We have a habit of assuming that if other civilizations existed, they would eventually be noticeable everywhere. But networks do not work that way. They are not uniformly dense. They have hubs, corridors, dead zones, bypasses, regional clusters, strategic choke points, and neglected outskirts. Two places can exist in the same larger system and have radically different experiences of connection. One becomes a crossroads, the other becomes a cul-de-sac. One hears constant motion, the other hears wind. The Milky Way may be exactly that kind of structure, dense and rich toward the center, sparse and disconnected toward some outer regions, thick with usable nodes along certain stellar histories, thin and awkward along others. If Earth formed in one of the quieter margins, then the silence we feel may not be a cosmic verdict at all. It may be geography, or more precisely, topology. We are not hearing nothing because there is nothing to hear. We are hearing very little because the roots that matter do not naturally pass through here. That possibility reshapes the emotional meaning of being human at this moment. It suggests we may not be standing at the center of the question. We may be standing near its edge. A young species in a relatively quiet neighborhood, only now beginning to suspect that the major corridors of galactic motion lie elsewhere, braided through black hole populations and dense central zones. We have spent most of our history fearing rather than understanding. If so, then the real frontier is not just learning how to travel. It is learning how to relocate our imagination from stars as destinations to black holes as infrastructure. That is a much stranger psychological leap than people appreciate. For all of human history, stars have represented guidance, beauty, continuity, aspiration. Black holes have represented annihilation. To accept the black hole network as the true architecture of interstellar movement is to reverse something deep in our symbolic map of the universe. The things we love to look at may not be what carry civilization forward. The things we feared to imagine may be the actual doors between worlds. And if that inversion is real, then the species that succeeds in crossing the galaxy is not merely one that grows more capable. It is one that grows less sentimental, less attached to the gentle picture of a universe lit by friendly suns and empty between them, more willing to accept that the infrastructure of reality is built out of violence, collapse, and curvature so extreme that light itself is forced into obedience. It is not a comforting image, but comfort has never been a reliable guide to truth. There is another implication here too, and it may be the hardest one. If the black hole network functions as a filter, then passing through, it may not just change a civilization's transportation. It may change its values. Civilizations that organize themselves around survival near catastrophic environments would almost inevitably reward very different traits than civilizations that remain planet-bound. Patience at enormous scales, redundancy everywhere, tolerance for delay, comfort with autonomy, emotional adaptation to isolation, a design culture built not around convenience, but around failure containment under impossible conditions. That does not just produce different machines, it produces different priorities. Such civilizations may become difficult to recognize not because they are hiding, but because they have become alien in the most literal way, shaped by pressures we have not yet lived through. Even their concept of neighborhood may be different. To us, nearby stars feel adjacent. To a civilization using gravitational routing, near may mean something entirely different. A system 50 light-years away on a well-connected corridor may be functionally closer than a system 5 light-years away in a sparse region with no useful nodes. A galactic center hub may feel more central to daily movement than local stars visible in the sky. Their maps, their trade, their strategy, their myths, their fears, all of it would be organized around a topology most emerging civilizations would not even know existed. In that sense, learning about the halo drive is not just learning a propulsion concept. It is learning that the galaxy might already have a hidden geography, one that intelligent life must eventually discover if it is to stop being provincial. The stars tell you where the matter is luminous. The black holes tell you where motion becomes possible. And now, the silence begins to look almost cruelly misleading, because from inside a quiet system, one naturally assumes quiet is the condition of the whole. That is what isolation feels like from the inside. It feels universal. It feels final. It tells you a story. Nobody is there. Nothing is moving. The dark between stars is mostly empty of intention. But if the roots lie elsewhere, then isolation is not a fact about the whole galaxy. It is a local experience produced by being borne away from the road. There is a kind of humility in that realization, and a kind of urgency. Because if this picture is even partly right, then our future hinges on whether we can transition from observers of black holes to users of them. Not recklessly, not tomorrow, but eventually. The first civilization in a quiet region that learns how to survive the nodes does not just build a faster ship. It changes its relationship to the galaxy. It ceases to be trapped in a local pocket and becomes legible at a larger scale. It joins the topology. It acquires a direction the stars alone could never give it. That is why this is not really a story about propulsion. It only looks like one at first. Underneath, it is a story about admission, about what the universe demands before it lets a species move from curiosity to participation. The equations are known, the mechanisms are plausible, the infrastructure is already there. The unresolved question is whether intelligence, once it evolves somewhere soft and temporary, can harden itself enough to function where the real doors are. And perhaps that has always been the question. Perhaps every civilization eventually comes to the same threshold. It masters chemistry, then atoms, then information, then local space. It looks outward and sees impossible distances. It dreams of shortcuts. It imagines new physics. Then, if it is lucky and patient and rigorous enough, it discovers what the universe was offering all along, not a shortcut, but a route, a terrible route, a precise route, a route with conditions so severe they almost look like a refusal. And then that civilization decides what kind of civilization it is, one that turns away, or one that learns how to live beside event horizons. If that sounds dramatic, good, it should, because the stakes really are that strange. The road to the stars may not be blocked by ignorance. It may be blocked by temperament, by whether a thinking species can accept a future in which the ordinary image of safety no longer applies, by whether it can build not just stronger tools, but a stronger tolerance for operating where every instinct says, do not go there. And once that becomes clear, our own place in the story feels less settled than before. We are not asking anymore whether the universe permits interstellar travel. It does. We are not even asking whether there are enough energy sources. There are. We are asking something sharper now. When the road finally reveals itself, and it turns out to begin at the edge of the most destructive objects in existence, what kind of species keeps walking? That is where the problem stops being technical and becomes civilizational in the deepest sense. Because the answer is not going to come from a single invention. It is not going to arrive in the form of one miraculous engine or one genius insight or one generation of engineers suddenly deciding to be bold. A road like this changes everything around it. It changes what counts as preparation. It changes what counts as maturity. It changes what a society must be able to endure before it can even attempt the crossing. We tend to imagine technological progress as a staircase, one level above the last. More power, more efficiency, more knowledge, more reach. But the road we have been tracing through black holes does not behave like a staircase. It behaves like a threshold. Below a certain point, you are still a local civilization, no matter how sophisticated you become within your local bubble. Above that point, you become something else. Not because you know more equations, but because you have built a system that can operate where failure is final and where the environment is indistinguishable from catastrophe. That threshold may explain more than just the silence. It may explain why the galaxy, if inhabited, does not feel crowded. Because once you start thinking in terms of thresholds instead of simple progress, you stop assuming that intelligence naturally spreads everywhere. You stop imagining that any species with enough time will inevitably fill the stars. Time helps, yes. Intelligence helps, yes. But neither one automatically grants access to the network. A civilization can flourish for millions of years around its own star and still never cross the threshold. It can become wise, artistic, computationally powerful, biologically refined, maybe even immortal by its own standards, and still remain trapped inside a quiet region because the step from ordinary spacefaring to black hole-capable transit is not a continuation. It is a transformation, and transformations fail all the time. This is one of the most underappreciated facts in the history of life and technology alike. The world is full of processes that look inevitable in hindsight and almost never happened in practice. Multicellular life took billions of years. Complex nervous systems took longer. Intelligence, perhaps once in countless biological experiments, perhaps rarely even where conditions were favorable. The appearance of a capability does not guarantee its continuation. It only proves that continuation is possible. So if the black hole threshold is genuinely as severe as it looks, then maybe only a tiny fraction of intelligent species ever pass it. Not because they are stupid, not because they lack ambition, but because the environment required to proceed is so hostile that the number of civilizations willing and able to redesign themselves around it may be vanishingly small. That would make the galaxy a very different place from the one imagined in simpler science fiction. Not a densely settled sea of obvious empires, not a uniformly inhabited spiral of glowing civilizations, something patchier, more topological, more conditional, a few corridors of traffic, a few powerful hubs, great quiet regions in between, vast populations of local intelligences that never join the deeper roots. And perhaps scattered among them some smaller number that did. It is worth pausing on how strange that would feel from the inside. Imagine being born in a place like ours, a normal star, a few planets, a sky full of light. A history built around sunlight, weather, seasons, visible horizons. Everything about your species, its myths, its fears, its architecture, its language, shaped by conditions that reward stability and punish extremity. Then, after centuries of science, you discover that the only practical road to the stars is not through the gentle lights that guided your ancestors, but through collapsed objects so extreme they erase the meaning of gentle altogether. Through regions where light bends into loops, where time desynchronizes, where radiation saturates matter, where gravity becomes structure rather than force, where the difference between success and irreversible death may be measured in kilometers or milliseconds. How many societies, upon learning that, say yes, really yes, not in imagination, not in speeches, not in fiction, in policy, in design, in resource allocation, in long-term cultural commitment? How many decide that the future of their species should be built around surviving the environment's evolution spent millions of years teaching them to avoid? This may be where the true bottleneck lies, not in physics, in commitment. Because the deeper implication of all this is that interstellar movement, if governed by black hole infrastructure, becomes a moral and cultural choice before it becomes a transportation system. It demands not only knowledge, but willingness to reorganize an entire civilization around delayed reward, catastrophic risk, and environments that offer no sympathy. The local world stops being the unquestioned center of meaning. The network becomes the horizon. The young are raised not just to understand the stars, but to understand roots. The sciences that matter most cease to be those that merely describe distant objects and become those that let you inhabit impossible neighborhoods without dying. At that point, astronomy and engineering merge into destiny. And perhaps that is exactly what we are beginning to glimpse. Not just a propulsion proposal, but a direction in which a species must bend itself if it wants to matter at galactic scale. The phrase sounds grand, but it points to something almost brutally simple. A species matters at galactic scale when it can move through galactic structure rather than merely observe it, when it can do more than look at black holes with awe. When it can use them, that is the dividing line. Below it, civilization remains interpretive. Above it, civilization becomes kinetic. And if that is true, then even our current scientific era begins to look like a prelude. We are proud of our instruments, and rightly so. We have measured gravitational waves, imaged event horizon shadows, tracked stars orbiting invisible masses, sent machines beyond the heliosphere. All of that is astonishing. But from the perspective of a species already inside the network, these may look like the first clumsy gestures of a child touching the map without understanding the roads. We know black holes exist. We know binary systems exist. We know curved spacetime can redirect light. We know moving gravitational systems can exchange energy. We know enough, in other words, to recognize the outline of the infrastructure. What we do not yet know is whether we can survive entry. That is why the next era, if it comes, will not merely be an extension of astronautics. It will be a survival science, a discipline of operating where ordinary assumptions fail, materials that remain coherent under tidal stress gradients, shielding architectures that handle not just high radiation, but long exposure under mass constraints, guidance systems able to navigate dynamic relativistic geometry without external intervention, autonomous habitats able to preserve mind and body in total operational isolation. Not pieces of a spaceship in the old sense, components of a self-sustaining presence in the one class of environment that can actually open the galaxy. A presence, not just a vehicle. That distinction matters because the closer you get to the network, the less plausible a simple ship begins to look. A ship implies passage, a temporary transit through a dangerous place on the way to somewhere else. But black hole infrastructure may demand something more like occupation. Staging systems, relays, hardened autonomous platforms, ways of anchoring knowledge and capability near the nodes themselves. If the important routes are organized around difficult gravitational environments, then any mature interstellar civilization might be forced to do what every transportation civilization eventually does. Build logistics where the bottlenecks are, ports, depots, service habitats, navigation arrays, energy transfer platforms, maybe not all at once, maybe not at first. But eventually, if traffic becomes meaningful, infrastructure grows around infrastructure. And that is a thought worth holding for a moment, because it means black holes may not merely be the engines of interstellar movement. They may become the places where civilization thickens, not planets, not even ordinary stars. The densest concentrations of technological activity in the galaxy could end up clustering around the very objects we still talk about mostly as endpoints of collapse. The deadest things in the universe becoming the busiest. If that sounds inverted, it is. But inversion has been the pattern all along. Empty space turns out not to be empty. Destruction turns out to be utility. Silence turns out to be local. Distance turns out not to be the real obstacle. The stars turn out not to define the roads. Nearly every intuitive picture breaks the deeper you go. Even the idea of a destination begins to change. In ordinary thinking, a destination is a place where you stop, a world, a system, a colony, a home. But on a black hole network, destinations may become secondary to access. A place that lacks a usable route may be strategically less important than a harsher place that sits at the junction of multiple corridors. Worlds rich in beauty or resources may matter less than nodes rich in connectivity. The logic of settlement shifts from comfort to topology. Again, we have seen this before on smaller scales. Human history is full of cities that became powerful not because they were the nicest places to live, but because they sat where movement converged. Now scale that truth to the Milky Way. The centers of gravity-rich networks become the places that matter. And suddenly, the galaxy starts to look less like a scattered archipelago of worlds and more like an enormous transportation ecology whose dominant features are hidden from the naked eye. We have been staring at the lights and mistaking illumination for importance. The important places may be the dark ones. That leads, inevitably, to the most uncomfortable possibility of all. If other civilizations already understood this, then perhaps the evidence is not merely subtle because we are looking in the wrong data. Perhaps it is subtle because mature civilizations gradually migrate away from the kinds of places where young civilizations expect to find them. They may still visit stars, harvest matter, study biospheres, seed archives, conduct science, perhaps even watch emerging worlds. But their center of mass, their real infrastructure, their deepest mobility, their strategic core may drift toward the nodes, toward the black hole corridors, toward the galactic hubs, away from the bright provincialism of ordinary stellar neighborhoods. If so, then every popular image of the cosmic future is backward. The future is not a glowing spread of worlds under warm suns. It is a cold, distributed, gravitational civilization using stars as local resources and black holes as the architecture of movement. And from where we stand now, that future would be almost invisible, not because it is hidden from us on purpose, but because our eyes, our instruments, our questions, and our hopes were all trained on the wrong landmarks. There is a sadness in that, but also a kind of relief, because once you stop expecting the universe to be loud in familiar ways, the silence becomes less personal. It stops sounding like rejection. It starts sounding like mismatch. We asked the sky for conversation when the sky may be organized around transit. We listened for declarations when the real signs may be timetables, route efficiencies, and the controlled abuse of orbital momentum near objects we only recently learned how to detect properly. We wanted neighbors waving from the porch light. The galaxy may be full of freight lines running through the dark, and then the question returns to us with new sharpness. What do we do with this knowledge now, if it is even partly right? The first answer is obvious and difficult. We keep learning how black holes really behave, not just as objects of theoretical interest, but as potential infrastructure. We refine our models of binary populations. We study orbital distributions. We improve gravitational wave observatories. We map the dense regions of the galaxy not merely by visible matter, but by connectivity potential. We begin, in other words, to ask a new class of questions, not only what is out there, but what is usable out there, not only where are the stars, but where are the nodes. And that change in questioning may matter as much as any future engine, because civilizations are shaped by what they decide is worth measuring. For most of history, the sky was a calendar, then a clock, then a laboratory. Perhaps the next step is to see it as infrastructure, to understand that the universe is not just something to know, but something to root through, if, and only if, you can survive the places where routing becomes possible. That is a harder vision of the future than most people want, but it may also be a more honest one. The universe has never promised comfort, only coherence. And coherent is exactly what this picture becomes the more you follow it. The energy problem points to black holes. The motion problem points to moving binaries. The routing problem points to network topology. The silence problem points to location and filters. The civilizational problem points to transformation under extreme conditions. None of these pieces feel pleasant, but they fit. They fit with an almost unnerving consistency. And when too many harsh pieces fit together cleanly, you are usually no longer looking at coincidence. You are looking at structure. Maybe that is the real message buried in all of this. Not that the answer to interstellar travel is romantic. Not that the universe was built to welcome us, but that there is, in fact, an answer, a brutally specific one. An answer that does not depend on miracles, only on whether life can become hard enough, patient enough, and precise enough to use what gravity has already laid down. That is both better and worse than fantasy. Better because it means the road is real. Worse because it means the road has standards. And someday, if we are still here, if we are still curious, if we are still willing to let reality reshape our dreams, instead of demanding that dreams reshape reality, we will have to decide whether and that decision, when it finally arrives, will not feel like the triumph people imagine. It will not be a clean cinematic moment, not a countdown, not a launch, not a flag planted against a foreign sky while music swells underneath it. If this is really the road, then the species that reaches it will not arrive there because it was intoxicated by romance. It will arrive there because it learned how to look directly at the hardest version of reality and keep going anyway. That is the real shape of the future hidden inside all of this. Not wonder replacing fear, wonder surviving fear, because fear in this story is not irrational, it is not weakness. It is the correct emotional response to the environments we are talking about. A black hole should frighten you. A photon sphere should frighten you. A binary system shedding energy through spacetime itself should frighten you. Radiation fields that can erase you faster than thought should frighten you. Tidal gradients that can turn structure into debris should frighten you. There is no maturity in pretending otherwise. The maturity is in what you do after you admit that the fear is justified. Do you step back and decide that some distances are not meant to be crossed? Or do you accept that the universe has written its roads in a language far harsher than anything life would have chosen for itself, and decide to learn that language anyway? That may be the clearest dividing line of all. Not intelligence versus ignorance, not courage versus cowardice, but one kind of civilization against another. One that insists the future must look emotionally acceptable before it can be pursued. And one that gradually understands that reality never signed that agreement. This is why the whole question feels so much bigger than propulsion, because propulsion is only the surface. Underneath, it sits something more fundamental. Whether life can outgrow the environmental logic of its birthplace. Whether a species born under one star can become something that is not psychologically or materially dependent on the conditions of that star. Whether beings shaped by warmth, cycles, atmosphere, and local sunlight can make peace with a future organized around darkness, delay, relativity, and gravitational violence. That is not just a transportation challenge. It is a redefinition of home. And maybe that is the hardest thing to absorb. We talk so easily about reaching the stars, but hidden inside the phrase is an assumption that the stars themselves remain central. That they are the natural destinations, the natural anchors, the natural meaning makers of the galaxy. But if the picture we have traced is right, then the stars may be where life begins, not where it ultimately organizes itself. The stars are nurseries, local economies, islands of habitability. The deeper architecture, the thing that actually allows movement at scale, belongs to black holes, binaries, hubs, corridors, and regions of warped geometry so extreme that they barely resemble the universe human intuition evolved to navigate. So perhaps the true path outward is not a path from star to star. Perhaps it is a path from star-born life to gravity-born civilization. And that is a much stranger transformation than most of our stories ever prepared us for. Because it implies that a truly interstellar species does not simply expand. It migrates conceptually. It leaves behind not just a planet, not just a solar system, but an entire emotional picture of what the universe is for. It stops expecting the cosmos to reward innocence. It stops demanding that the road be gentle. It learns to value access over comfort, structure over scenery, survival over symbolism. It does not stop loving the stars, maybe, but it no longer mistakes them for the thing that makes the galaxy traversable. And once that shift happens, the rest follows. Research changes, infrastructure changes, education changes, politics changes, even time changes. Because a species that begins planning around routes measured in decades, around nodes whose importance depends on orbital dynamics and gravitational stability, around operations where communication lag erases the fantasy of real-time oversight, that species begins to think differently about continuity itself. It becomes less addicted to immediacy, less dependent on local feedback, more capable of building systems meant to endure long enough for their creators never to see the final result in person. That kind of civilization would not be built quickly. It would have to learn patience at scales that feel inhuman from where we stand now. But then again, maybe that is exactly the point. Interstellar civilization may not be what happens when a species gets powerful. It may be what happens when a species gets patient enough to survive power, patient enough to distribute itself, patient enough to design for conditions rather than preferences, patient enough to stop asking the universe to be nicer than it is. And if that sounds severe, consider the alternative. Consider the possibility that this is simply what reality has always required, and we are only now old enough to notice. For most of history, humanity has lived inside protective layers we did not build. Atmosphere, magnetosphere, gravity wells gentle enough to support stable bodies and stable cultures. Even our first steps into space happened inside the shadow of home, within reach of return, within environments still partly buffered by the planet that made us. Everything about our current idea of exploration still carries the emotional residue of safety. The ship goes out, the crew comes back. The mission is dangerous, yes, but framed by support, rescue, continuity. Interstellar movement abolishes that framing. Black hole routing obliterates it. At that point, exploration stops being a controlled excursion and becomes a state of existence. A craft near a node is not away from home in the old sense. It is in the only class of place where access to the larger structure is possible. The route is not a detour through danger on the way to civilization. The route is where civilization begins to happen. That is why the final question in this story is not really whether the halo drive works. The mathematics suggests some version of it can. The physics permits the logic. The astrophysical infrastructure exists. The final question is whether anything made of life can endure what the answer asks of it, not once, not heroically, not as an exception, routinely. Civilization is not built out of exceptions. It is built out of repeatability, out of systems that work again and again under pressure. So the true test is not whether one mission could survive one impossible maneuver near one black hole. The true test is whether a species can make the impossible ordinary, whether it can turn the exception into procedure, the terror into training, the edge case into infrastructure. That is the moment the galaxy would change. Not when the first equation is written, not when the first simulation runs, but when the first civilization proves, in practice, that the route can be used more than once. Because after that, the network is no longer theoretical. It becomes historical, and history compounds. One successful node leads to a staging system. One staging system leads to mapping. Mapping leads to corridors. Corridors lead to favored hubs, logistical standards, route conventions, traffic priorities, whole new categories of technology optimized not for surviving planets, but for surviving transit. The network stops being a possibility and becomes a geography. And once it becomes geography, everything we asked at the beginning returns in a new form. Where is everybody? Maybe along the corridors. Why don't we hear them? Maybe because corridor traffic does not sound like conversation from the shoulder of the road. Why does the galaxy feel so empty? Maybe because emptiness is what quiet topology feels like from a local node with poor connectivity. Why haven't they come here? Maybe because here is not especially central in the map gravity cares about. Those are not final answers, but they are better questions than the ones we began with, more disciplined, more faithful to the structure of the universe that the physics seems to be revealing. And there is something strangely hopeful in that, even if the hope is colder than the version we were taught to want. Because this picture does not say the stars are forever beyond reach. It says reach has terms. It says the universe is not withholding the road. It is specifying the cost of entry with unforgiving precision. Learn to survive the nodes. Learn to navigate moving geometry. Learn to design for radiation, autonomy, delay, and irreversible error. Learn to operate where your instincts fail. Learn to build continuity in places that do not care whether continuity is convenient. Do that and the map opens. Fail, and your civilization remains local no matter how brilliant it becomes under its own sun. Maybe that is why this idea lingers in the mind the way it does, because it is neither fantasy nor comfort. It does not promise salvation through a miracle technology. It does not flatter us with the assumption that intelligence alone is enough. It does something harder. It places us inside a universe whose structure is coherent but indifferent, and asks whether we are capable of adapting to coherence without demanding kindness. That is a very different kind of hope. It is the hope that reality, even at its harshest, still contains a path, not an easy one, not a merciful one, but a path, and perhaps that is enough. Perhaps the most important thing is not that we have not reached it yet. Perhaps the most important thing is that, for the first time, we can begin to see what the road might actually be, not as myth, not as metaphor, as a real possibility written into the same physics that bends starlight, slows clocks, rings space-time, and shadows black holes against the background glow of the cosmos. A real path, built from collapse, powered by motion, guarded by conditions so extreme they almost read like a warning. And maybe they are a warning, but not a prohibition. Warnings tell you what something costs. They do not tell you it cannot be done. So now, after all of this, we arrive at the only conclusion that matters. Interstellar travel may already be solved in principle. The road may already exist. The engines may already be out there, spinning in the dark, waiting in binary pairs, tracing corridors through the Milky Way with all the patience of gravity itself. The silence may not mean we are alone. It may only mean we have not reached the road. And the future of our species may depend less on discovering new physics than on deciding whether we are willing to become the kind of civilization that can use the physics we already have. That is a harder truth than fantasy, but it is also, in its own severe way, a more beautiful one, because it means the galaxy is not closed, it is waiting. And somewhere between our fear of what black holes are and our understanding of what they can become lies the next great decision in the history of life. Not whether the stars can be reached, but whether we are ready